Ken is beginning a series of talks in the manual Technical Presentations. These presentations are aimed at different audiences. Tonight's project presentation, the technical briefing, is aimed at informing a group of technical managers. Control your excitement. Or an advisory board or review panel about what scientific work is being conducted. So imagine you are a member of one of these groups. Still, hold down the excitement. And now learn what Ken does in his laboratory at UIC. And now join me in welcoming Ken.
Suppose it's your responsibility to design a clean and efficient aircraft engine. Something you might want to do. If that were your job, you might find that overwhelming because you know that the kinds of fuels that aircraft engines burn are extremely varied depending what the petroleum source is, or they may have an unusual composition if they're made from bio-derived sources, or if they're a synthetic fuel. And if you're a designer, you might think, how am I going to design an engine like this for a clean burning fuel if the fuel could contain maybe 100 or even 1,000 different chemical components? And fuels do contain sometimes thousands of different chemicals. There is an easier way to design an engine for a practical fuel, and today you're going to learn how we do that in my laboratory. Considering that fuels have hundreds, if not thousands, of things in them, there's no way an engine designer is going to find out how each one of those things burn. But if it were possible to find 3 or 4 chemicals that together burn just like a fuel, then you would have a surrogate fuel, one that stands in for the actual fuel, that if you knew its behavior, you would know how a real fuel behaves. And what we do in my laboratory is develop and study surrogate fuels. So if you are concerned about your job, designing an engine for just any fuel, don't worry. Today you're going to learn in my lab, and I'll talk more about my lab later, where you can get the information to work with any kind of fuel by working on a surrogate fuel. Now, just recently, I had a project that was supported by the Air Force Office of Scientific Research to develop just such a surrogate fuel for a common jet fuel called Jet A. Very simple, jet, letter A. This is a typical Air Force fuel, but it can be of many different chemical compositions as long as it meets certain requirements. What we did in my laboratory is we found 4 compounds. One was a 12-carbon straight chain called dodecane. The second one was an 8-carbon branched species called isooctane. You might be familiar with that from your gasoline. You've heard about octane number. It's that isooctane. The third and the fourth were aromatic compounds, in part because they smell and not so nice, so aromatic's a misnomer, but also because they contain a benzene ring in it. And one was N-propylbenzene, and one was trimethylbenzene. So we had these 4 compounds, the dodecane, the isooctane, the N-propylbenzene, and the trimethylbenzene. And these were the surrogate fuel components that would provide engine designers the chemical information they need to design engines. Do you find this interesting? You want to know more?
Absolutely.
Yeah! All right. Would you like to know how we study these surrogate fuels? I hope so, because I'm about to tell you. In my laboratory, we have a special device called a high-pressure single-pulse shock tube. Now, it's shown in this slide, and since I didn't know tonight if the slides were going to work, we didn't arrange the room for you to see it that well. So afterwards, if you'd like, you can come up and take a closer look. But my laboratory has this large-scale shock tube, which, as the name suggests, there's something that shocks in there. And what's shocking about that shock tube is that it creates a shock wave when a metal diaphragm breaks between a high-pressure section and a low-pressure section that causes a shock wave to pass down the tube and heat up the material that we want to react. And the material that we want to react is one of these jet fuel components in the presence of oxygen. But just to give you an idea of what this shock tube involves, one of my first students was a very small Indian woman named Piali Sakar. Really small. So small that to work on this tube, she had to get on a ladder and try and reach around this thing to make it work. We had to build a special wrench with a long handle so she could go like that and open it up and make the device work. So it's a big tube, a lot of heavy metal, big bolts, very mechanical engineering. And it is done in a mechanical engineering department. And so what we do with this tube is we shock heat one of these surrogate fuels and the combinations of them together, and then we take out samples of what's in the tube after the fuels have reacted, and we find out what's in that gas mixture. What's in there are fragments of the original fuel after it's reacted with the oxygen, because the fuel starts out as a big molecule, breaks down to a small one, then a small one, then a smaller one, and eventually it's carbon dioxide and water. Now you might be wondering, well, if it goes to CO2 and water, why do we have to know all these little steps? All we care about is we burn this stuff and out comes water and CO2, which messes up the atmosphere, and we could just deal with that separately. The reason it's important for you as an engine designer, if that's who you're pretending you are, is that those chemical species that go from the fuel to the next step, to the next step, to the next step, are what's emitted from a polluting engine. And by knowing the step-by-step progress, we can provide you, an engine designer, knowledge about what is actually formed as a pollutant from that particular fuel. Furthermore, if something is being formed as a pollutant and being emitted from the engine, it means that the fuel is not burning efficiently. It is not being converted completely to CO2 and water. So if your job is to design an engine that's clean and efficient, then knowing what the individual species are is important for the design. And the shock tube is the means for figuring out what the individual species are. So we take the species out, and we have a special device called a gas chromatograph mass spectrometer, which will tell us the identity of every single species and how much there is in the mixture. From that, we then have the information to build a computer model. Now, if you were a designer, and I were to tell you, well, some ethane is formed, some ethylene is formed, maybe some butadiene is formed from this fuel, you might find that helpful, but what you would really want to know is how can I predict that? You might say, Ken, give me a tool, a computer model, something that I can use to calculate what comes out of my engine. And that's what we do in my laboratory. So after we run the shock tube, we take the sample out, we analyze what's in that sample, we then sit down and put numbers to the chemical reactions and rate constants that go with these reactions so that species can be predicted that come out of the shock tube, and by coming out of the shock tube, coming out of the engine. So we generate computer models that we then provide to engine designers and anyone who needs this kind of information. So in my laboratory, we conduct experiments in a high-pressure shock tube. We analyze what's formed from the fuel that's oxidized, combusted, and then knowing what's formed, we build computerized models that can predict what's formed and then provide that to the scientific public in the form of articles that we publish in the general literature. So when I opened, I said, imagine you might be an engine designer who feels overwhelmed by the prospect of designing an engine that has to accommodate fuels with maybe thousands of things in it. And now, perhaps you've learned that there is a way to do that. Come to me. I'll do a study in my laboratory on maybe 4 special compounds that could replicate this fuel, provide you with a model, you integrate it into your design, and then you say, thank you, Ken. Thank you, Tim.